Simple harmonic motion. We are surrounded by oscillations, motions that repeat themselves, such as guitar strings, drums, bells, diaphragms in telephones and speaker systems, and quartz crystals in wristwatches. Less evidence are the oscillations of the air molecules that transmit the sensation of sound, the oscillations of the atoms in a solid that convey the sensation of temperature, and the oscillations of the electrons in the antennas of radio and television transmitters. Oscillations are not confined to material objects, such as violin strings and electrodes. Light, radio waves, X-rays, and gamma rays are also oscillatory phenomena. You will study such oscillations in later chapters and will be helped greatly there by analogy with the mechanical oscillations that you are about to study here. Oscillations in the real world are usually damped. That is, the motion dies out gradually, transferring mechanics energy to thermal energy by the action of frictional forces. Although we cannot totally eliminate such loss of mechanical energy, we can replenish the energy from some sources to compensate for the mechanical energy loss to friction. Simple harmonic motion. Any motion that repeats himself at regular intervals is called periodical motion or harmonic motion. Simple harmonic motion, SHM, is a kind of periodical motion, which is a sinusoidal function of time. X at time t equals xm cosine omega t plus phi. This is a sinusoidal. Sine is okay too. If the particle vibrates back and forth, at this time, we extend it at a time, we find it like this one. And if we turn 90 degrees, we get this one. This is time, this is this x, okay? In this case, first thing, the cosine is phi is 0. Why? Because at t equal to 0, this is 0. At x equal to xm, that means this is 0, okay?
Tuning forks create sound waves because of the side-to-side motion of their tines. But what is the exact form of that motion? We'll use this floppy version of a tuning fork with a light mounted on one of the tines to find out. When we set the fork vibrating and sweep it past the camera, the path of the light is a sine wave.
Simple harmonic motion. X at time t is xm cosine omega t plus phi. Well, this is called displacement at time t. This xm is the maximum displacement. You call it amplitude. This number is defined as a positive number, okay? And cosine changes between -1 and 1. This omega we call the angular frequency. And the total omega t for phi we call the phase. This is the angle, okay? This time t, this is called phase constant, or the initial phase, when t equal to 0, the initial phase. Frequency, or the numbers of oscillations that are completed each second. Okay? For example, called 10 hertz, that's 1/2. In 1 second, how many times you have 10 oscillations? Okay. 1 hertz means 1 oscillation per second. Period, the time for 1 complete oscillation. The period equal to 1/f. For example, you have a frequency of 10 hertz. That means that 1 second you complete 10 oscillations. For each oscillation, it takes time 1/10. So the relationship between period and frequency is reverse. Okay, T equals 1/f, or F equal to 1/t. So this is a simple harmonic motion. X at t equal to xm cosine omega t plus phi. Now we look at this two, the blue one and the red one. They xm are the same because the maximum displacement, this is x, are the same. But they repeat themselves. One circle, the time are different. The time different. This is the blue one is this t. The red one is this t prime. So the period are different. For these two lines, you see the period are the same. Okay, maximum to maximum, maximum to maximum, minimum, minimum. Okay, but the amplitude are different. Okay, this is xm, xm prime are different. Look, these two, they have the same period, same magnitude, but it switched a little bit horizontally because of a phi. So the initial phase is different. The interpretation of an angular frequency omega. Well, the frequency is angular frequency. Well, the frequency is repeated. Okay, how many times you repeat in a second? The angular, so the angular frequency. We look at this one. Okay, we know the period are different, right? The amplitude are the same. T at time t, x at time t, you could xm cos omega t. Well, what we call frequency, we see the displacement xt must return to its initial value after one period of time t. Let's see, after one period, this one, repeat this one. Or you get here, you repeat it here, okay? At any time, this t must be any time. So we see, mathematically we see x with t equal to t plus period. This period. For the two period, the three period are the same. We use the shortest one period must equal to t. That's mathematics. The displacement is the same, x the same. And we put this one into this x, we get xm cosine omega t plus period t plus phi equal this t. This t is this t, so xm cosine omega t plus m. This t could be any time or any t, not particular. And then we compare these two equations. Xm can cancel out, so the phase inside omega t plus capital T plus phi must equal to small omega t plus phi plus 2n pi, n 2 pi, or 2 pi n. We take n equal to 1 because it's the shortest, the shortest time. So in this case, we cancel out phi. We get a t equal to omega t equal to 2 pi. In other words, omega is 2 pi over t, or t is 1/5 frequency. So this is equal to 2 pi f. Okay? What do you call it? We call it angular frequency. This is frequency. We put an angle, 2 pi. So to get 2 pi, angular frequency. This is how I remember that one. Okay? So this is three. Angular frequency, period frequency, they connect with each other. Once we know one, we can find another two. The unit is called the radius per period per second. Simple harmonic motion, SHM, has a property, its acceleration at time t equal to minus omega square x at time t. In other words, the acceleration is proportional to its displacement, with minus with constant. Now look at this one. This is a simple harmonic motion, sinusoidal displacement. Okay, sine or cosine. This is a curve. This is the cosine. This is x. This is a t. We find the v. What is the v? V is dx dt. And we do the derivative with the time t. Okay, the cosine derivative with time t is minus sine plus omega. Okay, so get the minus omega xm sine omega t plus phi. Okay, or we can write it v equal to v maximum minus v maximum sines. We put this one, this is sine and minus. So this is sine with a minus. Of course, this is time t, this is a v. Okay, this is a v. Okay, okay. And we do the acceleration. A equal to dv dt. Okay. And we do this derivative with respect to time t again. Sine derivative sine is cosine and omega. So get the omega squared. So A equal to minus omega squared xm cosine omega t plus phi. And look at this xm cosine omega t plus phi is exactly to x at time t. So we put this one here. It's minus omega squared t. Then you see we get the acceleration equal to minus omega squared t. Okay, this is a characteristic of simple harmonic motion. Okay, we plot this one. This is cosine too. So like that, this one, and it's have a minus. So reverse. Of course, the vertical is different. This is acceleration. This is velocity. This is displacement. Okay. Now we find the maximum v. This one v omega x. The maximum a is omega squared xm. Okay, omega squared xm. And that v is between these plus or minus. A is between the plus minus. Okay, the conclusion. When x equal to 0, this is 0. A is 0. V is maximum. Okay, A is 0. When x is maximum, x maximum cosine is 1, so A is maximum, V is 0. Okay. This is a simple harmonic motion. They are sinusoidal function. And we have acceleration of simple harmonic motion equal to minus x plus x omega squared. So in simple harmonic motion, the acceleration is proportional to the displacement, but opposite indirect sign. And the two quantities are related by a square of the angular frequency. These you have to remember. The fourth law for simple harmonic motion. We look at this F equal to ma. When you do the simple harmonic motion, F must satisfy this one. And the A is the second derivative of its displacement with respect to time t. Okay, and we know this one. We put this equation, we get is equal to minus omega squared x. This is a caret. The black one is the characteristic of simple harmonic motion. Its acceleration is proportional its displacement with omega squared. And we look at this f. This f is proportional to x. So that's like this is like the Hooke's law. Okay, Hooke's law is f equal to minus kx. So we compare these two. We find that k equal to m omega squared. Okay, and omega equal to k over m squared root. Okay. So we look at this one. This is this one. This block moves under the force of spring. The spring is satisfied. This one, it must have simple harmonic motion. And the omega, the angular frequency equal to k over m. K is the spring constant of the spring. M is the mass of this one. Okay. And the k is equal to m omega squared. This is the fourth law for simple harmonic motion. Simple harmonic motion must have a force which obeys the Hooke's law. The block spring system forms a linear simple harmonic oscillator at the oscillator, where linear indicate that f is proportional to x. So this is a linear function. And you plot it as a line, it's a linear, okay? Simple harmonic motion is the motion executed by a particle of mass m, subject to a force that is proportional to the displacement of the particle, but opposite in sign. Angular frequency, omega equal to k over m square root. When m is smaller, omega is larger. K is larger, omega is larger. Omega is larger, t is smaller, okay? So period t is 2 pi of c, 2 pi f omega of k, okay? This formula you have to remember. Every oscillating system, be it the linear oscillator of a diving bell or violin string, has some proper elements of springiness and some elements of inertia or mass, and thus resembles a linear oscillator. In other words, linear oscillator has two elements. One is springiness and one is inertia or mass. Oscillator, these elements are located in separate parts of the system in some linear oscillator. The springiness being entirely in a spring, which we assume to be massless, and the inertia being entirely in the block, which we assume to be rigid. But, however, in violin spring, the two elements are both within the spring itself, as you will see in other clips. This is a Hooke from UK.
This heavy spring and this set of masses will be used to show simple harmonic motion. If we place 1 kilogram on the spring and set it in motion, the spring and weight oscillate with a regular period. What will happen to the period of oscillation if we increase the mass to 2 kilograms? The period increases. If we put an identical spring side by side with the first spring and repeat the demonstration, how will the period of oscillation change? The period decreases.
We'll use this glider floating on a cushion of air and these springs to investigate simple harmonic motion. If a spring is attached to each end of a glider, the glider will oscillate back and forth on the track. What will happen to the period of oscillation if we double the mass of the glider?
The period double.
The top half of the screen shows the original arrangement, while the bottom half shows the glider with twice the mass. The period has increased. What will happen to the period if we add another spring to each end of the glider instead of more mass? The top half of the screen now shows the original setup, while the bottom half shows the glider with another set of springs attached. The period has now decreased. To show the form of this type of motion, we will mark 1 point on the glider and use it to draw a graph of position versus time.
Sample. A block whose mass m 680 grams is fastened to a spring whose spring constant K is 65 Newton per meter. The block is pulled a distance x 11 centimeter from its equilibrium position at x0 on a frictionless surface and released from rest at t equals 0. Question 8. What are the angular frequency, the frequency, and the period of the resulting oscillation? We said before, angular frequency, and the period, they are related with each other. So once we know one, we can find another two. Okay. By definition, omega equal to square root k over m. In this question, k is 65, m is 0.68. So remember, this one you have to use the standard unit called a kilogram. Okay. So we get omega. Once we get omega, we get a t, get a f. Okay. F equal to omega over 2 pi. Okay. And t equal to 1 over f, or 2 pi over t. T pi omega. We get this one. This is simple harmonic motion. What is the amplitude xm of the oscillation? Xm is 11. Okay? It's the maximum from energy conservation. What is the maximum speed Vn of the oscillation block, and where is the block when it occurs? Then we see the maximum velocity is omega xm. So we put number inside. When it happens, maximum is V is sine. When sine is maximum, cosine 0. So it happens when x at t equals 0. Anytime when x equals 0, you get a maximum V. What is the magnitude am of the maximum acceleration? Well, the acceleration is omega squared xm. You can find this one. Okay, where is it? X maximum, am is maximum. Okay. What is the phase constant phi for the motion? Then we know that when this is 11, this is 11, so this must be 1. Time to go to t, okay, and so the phi must be 0. Phi must be 0. Okay. What is the displacement function xt for the spring block system? Then we find everything, we put a number inside. Okay, so this is one formula. We put xm 0.11 with omega 9.850. So we get xm concrete explanation is 0.11. This is unit meter. Cosine 9.8 t second. Sample. At t0, the displacement x0 of the block in a linear oscillator, like that of above equation, is minus 8.50 centimeter. When we do the calculation, we must use unit meter, minus 0.0085 meter. This is what we read x0, we read as x at time z. The block's velocity v at time 0 is minus 0.920 meter per second, and its acceleration a at time 0 is positive 47 meter per second. Give you 3 initial condition. Question A. What is the angular frequency omega of its system? Omega equal to square k over m. We don't have this information in this question. What we do, we have 3. Okay? We know x at time 0 is this. Y at time 0 is this. A at time 0 it is. We know this one. This number, no. And we want to find omega. We look at this one. This is no omega. You have omega. You have omega. And if it's xm cosine, xm cosine. So we find out, we divided A0 minus divided x0. We can cancel out this one. We get omega squared. So you get this one. Then we get omega. Okay? Okay, once we get omega, see what else can do, right? The angular frequency is frequency equal to angular frequency divided by angle, 2 pi. You get this one. Once we get F, the reverse is the time t, okay? What is the phase constant phi at the amplitude xm? Now, we already omega, okay? We want to find the phi and xm. We look at this, v over this one. xm cancel out. We already have angular frequency omega. This is tangent theta. Okay? We get this one is tangent theta. So this number we know that. This one we know that. So can tangent phi. Tangent phi. Okay. Get this one and get a phi. This one you get a two angle. Either minus 25 or 150. Oh, this is you can go to 335 degree. Is which one is right, or both are right, or both are wrong? And we see this one. We put this xm at time t. We put the phi 1. So xm, we know this one. Cosine with the v, we get xm equal 9.4 centimeters. Then we check this one. We put cosine minus 1, and we put x0 and cosine minus, we get x this one. And we found this one is wrong. Why is wrong? Because our definition, the amplitude xn must be positive number, and there you get negative. So our answer is 150 degree. Energy in simple harmonic motion. We know x at t time t is xm cosine omega plus phi, and we know that when k equal to m omega squared. So let's see its potential energy. Potential energy a spring has equal to half kx squared, and we put x squared. We put this number. This is xm squared, cosine m squared, and put the k. And we know, and kinetic energy is half mv squared. V is derivative of x, we put it equal to minus omega xt, right? Yeah. So, okay, and we see this m omega squared. M omega squared equal to k. So this one equal to rewrite half k xm squared. Potential energy, kinetic energy. We look at this one, the coefficient are the same. So we put them together, we get a mechanical energy. So the mechanical energy E equal to U plus K. We put them together, this is take this off, and cosine squared plus sine squared anyway is 1. So we get mechanical energy at any location x is equal to half kx squared. Now, this is a constant because this is the maximum constant. And also we look at the t. At any time t, they are the same. Okay, it's different. It's any location, any time. Well, actually, they can be the same, right? Yeah, that's constant. An oscillating system normally contains an element of springiness and an element of inertia. It uses the former to store its potential energy. This is a springiness. And the latter, called the inertia, store its kinetic energy. We look at this one. This is x is vibrate, okay? This is time, okay? And x equal to 0, the potential energy is like this one, is 0. Okay. this is x equal to xm cosine omega t plus phi. And equal to kinetic energy equal to half mv squared. And when x equal to 0, v is maximum. See, this one, v is maximum. Okay, we put a v, this one is half kxm. Why the half k? Because you do the derivative, you have omega. And you square k omega square equal k omega square m omega square equal to k. So we put this one, we see, we put this kinetic energy and this potential always equal to this one. The total mechanical energy at any position is zero, is constant. Is constant. What is this? This is that when x is maximum, you don't have a speed. There's potential, total potential. And you look at this t. This is x, t. A t goes by, it vibrates at any time. The total mechanical energy at any time is constant too, as we see before. Sample. What is the mechanical energy E of the linear oscillator of above sample? Above sample. Initially, the block's position is 11 centimeter, and the speed v0. And spring constant k is 55. Mechanical energy is very easy because you have a k, we have xm, so it was equal the maximum position energy. Okay, remember that one. This one you have to use the unit, standard unit, meter. So 11 centimeter is 0.11 meter. Part question B. What are the potential energy U and the kinetic K of the oscillator when the block is at half? What are they when the block is at minus half? That's very easy. Very easy. The U equal to half mk. When the kx equal to half 4, this is energy. And this energy turned out the 1/4 total energy. And the leftover is the kinetic energy at this time. Okay? So it's about 3/4 E. This kinetic energy. Now, what is the kinetic energy and the potential energy at x equal to minus? Same thing.
Here is a device called a torsion pendulum. It consists of a flexible brass rod which is held tightly in an upper support and which has a heavy disc attached to its bottom end. If we twist the rod by rotating the disc and then release it, the pendulum oscillates. If we double the mass of the pendulum by adding this ring to the disc, how will the period of oscillation change? The period increases.